I'm Dr. Bob Arnott. Welcome to this course on machine learning in healthcare. You'll find a robust and wonderful set of tools to improve how you practice medicine as a doctor or better run a hospital as an administrator. This course will give you a fantastic overview of the key tools, easy to use platforms, and real world examples. At the end, we'll have real companies hiring machine learning experts. Whether you're looking for a career change or to acquire new and incredibly valuable skills, you'll find this course an incredibly interesting and fun starting point. We'll make everything crystal clear and simple so you'll be able to intelligently discuss machine learning with your colleagues and help your company, practice, or hospital move into the future with machine learning. So what is machine learning? Remember sitting in a restaurant as a kid with a paper placemat that had a whole series of dots and numbers you were supposed to connect? Remember that at some point, before you connected all of those dots, you would recognize the pattern and say, oh, aha, sure, I get it. That's a car, or a bear, or a tree. Well, machine learning is based on the ability of a computer to recognize a pattern in data without the need for you to program the computer to do it for you. The data literally writes the program instead of you, which is why having great data and clean data is at the heart of any machine learning project. I interviewed the head of Penn Medicine's Innovation Center. He said to me, hey, look, Bob, machine learning, deep learning, they're more and more becoming commodities, more and more off-the-shelf applications, more and more code available on sites like GitHub. What makes deep learning and machine learning work is great data. And in an Ivy League medical center, the data is great given the incredible quality of clinicians. So if you're in data science, focus on creating great data platforms and squeaky clean data sets. So just like you learned pattern recognition as a grade school or dining with your parents, pattern recognition gave birth to machine learning with a theory that computers can learn by themselves without the need for you to program them. And this could not be more fantastic for healthcare. Just as machines made human muscles 1,000 times stronger, machines will make the human brain 1,000 times more possible. And that's what Sebastian Thrun told The New Yorker. So you may still be saying, gee, I'm not a computer programmer, and this stuff looks way over my head. How can I possibly get any good at machine learning? Well, easy. More and more programs are plug and play with no programming. You just feed in the data and let her rip. Of course, like a sophisticated airplane on autopilot, you want to monitor the process and make fine adjustments to get better results. But it really can be that straightforward. So where artificial intelligence and machine learning has intimidated many of us and many businesses, the great little secret is it's becoming incredibly accessible. In this course, we're going to give you a solid foundation in the understanding machine learning in healthcare and its uses. But there is no need to program by writing computer code. Phew! You don't have to write a single original line of computer code. Promise. In later courses, we will give you cookbook code where you simply cut and paste the code into a working environment where you can add your own values and tune the model. You'll see a bit of that later, even in this introduction. Still, you won't have to do any original programming. To continue the airplane example, what really got the plane from A to B was very careful pre-flight planning. Pilots charted a course, checked the weight and balance, and fuel required. Preparing your machine learning journey depends on careful pre-planning, which largely involves preparing your data before you feed it into the system. So why is machine learning so vital to healthcare? The healthcare system as a whole has far too much information for anyone to analyze on a spreadsheet or even with standard statistical techniques. As an example, each one of us generates a phenomenal 2.4 gigabytes of data on our own every day. I love the term digital exhaust. Like a car spewing exhaust out of a tailpipe, we spew a steady stream of data exhaust all day long from our social media and iPhones, computer searches, wearable technology, medical tests, and health interactions. Now imagine you are a healthcare plan with 100 million insured. The amount of data is simply beyond comprehension for most of us. I did visit the largest insurer in the United States, United Healthcare, and discovered a giant room, 2 stories tall, that had these major health trends from all around the country on huge screens. They have a sophisticated data analysis program called Tableau that will comb through all the most critical data to look for important trends such as the arrival of flu season or spread of COVID and put it up in a highly graphical and understandable format. As doctors, nurses, and administrators, we can't even imagine what answers huge amounts of data will give to us. That's what's so exciting. Machine learning figures this all out and presents us these fantastic new patterns. What a thrill! There's a great aha moment like that kid in the restaurant. We look at him and say, it's a bear. A great recent example is the link between blood types and the propensity to become really ill with a COVID infection. Analyzing many patients in Italy showed a pattern no one expected. Type O blood types had a lower risk of becoming seriously ill with COVID. Another famous example is the link between inflammation and heart disease. We all thought heart disease was more related to cholesterol and high blood pressure, but it turned out as much as half was related to inflammation, and that led to a whole new way of thinking about treating heart disease. For instance, the cholesterol-lowering drugs ended up having a secondary benefit. They countered the effect of inflammation on the unstable plaques in your blood vessels so they did not break off, allowing cholesterol to spew into your arteries, causing a heart attack. One clue was the risk of heart disease decreased on cholesterol-lowering drugs before the cholesterol level hit bottom. Another reason that pattern recognition is so great for medicine is that this is how doctors think and why it's been so hard for AI to mimic this way of thinking. For example, as a doctor, I remember walking into an emergency room in upstate New York to see a patient in the early evening with acute chest pain. There's something odd about the patient's pain and its severity that made me think, this really isn't a heart attack. The first thing I did was to reach out for a pulse in the foot. There was none. In the first 45 seconds with this patient, I reached a provisional diagnosis of an aortic aneurysm. This is when a tear develops in the largest and most powerful blood vessel in the body and cuts off the critical blood supply to key parts of the body like the heart and, in his case, the legs. I called the cardiac surgeon at home and told him we had to get his team ready. We quickly ordered all the supporting tests. The key insight, though, was that there's this whole package of questions, medical history, physical diagnosis, x-rays, scans, catheterization, lab tests to support the diagnosis. But the main reason the machines have such a poor time emulating how doctors think is that we don't always actively deduce like a detective. We see a pattern, we recognize, and we act. In this case, the patient's life was saved by fast and preemptive actions. As we will see with machine learning, lives are saved with the ability to recognize patterns early. This may be seeing brain clots, warning signs of impending death in the ER, or making an early diagnosis of breast cancer. In each case, lives may be saved, efficiencies improved, and finances bolstered. So that's why I totally love data. The pure joy of the insights it gives me while making me a better doctor. You may rightfully say, hey, you love the action and excitement of surfing towering waves in the middle of the Molokai Channel, or racing up a 9,200-foot peak in the middle of winter on tiny race skis, or serving in war zones. What possible excitement is there in data? Well, the greatest excitement of all, when truly amazing insights emerge from the data. Data allows them to be so much smarter and make so much better decisions. There's a real thrill to seeing answers emerge from the data, giving us answers, insights, and actions we never even imagined. Just like a little kid looking at a ferocious bear emerging from the dots on his paper placemat, the key to medicine, and in fact any big industry, is the analysis of data, and it goes beyond simple insights. Have a look at this chart. This shows the progression from insights on data through descriptive analytics, which allows you to see where you've been. This gives you 20/20 hindsight, maybe a big oops. Here is this giant mistake we made we could have learned from. For instance, in the height of the COVID pandemic in New York City, up to 89% of people died on ventilators. A terrible tragedy. Diagnostic analytics allowed researchers to delineate what the problem was, high ventilator pressures, and formulate how it might be solved. The publication of a large study in JAMA described this. But what to do? Working with one of the world's great medical centers, I prepared a series of videos showing that high ventilator pressures led to these poor outcomes, almost literally blowing people's lungs up. Some required as many as 5 chest tubes from the damage done by these high pressures. Our film clearly laid out the rationale for lower pressures. These pressures would spare the baby or uninjured lung, so the patient had a fighting chance of recovery. So let's go back to this chart. The great value in the future The great value is to predict what will happen in the future, although the difficulty increases. Still, it's like predicting a train wreck. You're still going to have a train wreck. For instance, UCL London predicted 2.5 million American deaths from COVID, which left many of us anxious and even frightened. But we would still lose 2.5 million people. Now, take to the final step with prescriptive analytics. Go into lockdown and save 4,500 lives in 2 months. Then open up with universal mask coverage and careful social distancing. Save another 2 million lives. This is big data at its very best. In fact, staggeringly big data because you're prescribing changes for over 7 billion people across the planet. What a potential triumph. So to recap, the sequence is descriptive analytics, which gives you perfect 2020 hindsight, predictive analytics, which shows you what's likely to happen, and prescriptive analytics, which allows you to change the outcome. In medicine, nothing trumps outcomes. Researchers very carefully follow patients' results to see which treatments work best, which medical centers get the best possible results. I wrote a book several decades ago called The Best Medicine. At one medical center, a patient had an 18% chance of dying during cardiac surgery, only 0.9% at the Cleveland Clinic. Where would you rather have your operation performed? Making this data available made cardiac surgery safer for everyone because hospitals realized that their report card would improve their results. In an individual medical practice, motor learning can also make you a better healthcare provider. Here's an example. Researchers at Houston Methodist Research Center in Texas used a machine learning review to look at mammograms and found they could read them 30 times faster than radiologists and with 99% accuracy. Big data. Stanford estimates that in 2020, healthcare will produce 2,314 exabytes of healthcare data. How much is an exabyte? This is 1 billion gigabytes. 5 exabytes is equivalent to every word ever uttered in any language throughout the whole history of mankind. And that's why AI and machine learning is coming into its own, because this is the only way to look at numbers that big. What's intriguing about motor learning, and only when there were huge amounts of data was there enough to power AI, especially deep learning. What makes big data big? It's the common misperception that we have lots of data, therefore must be big, like a spreadsheet with 1 million rows. It doesn't. Big is not based on volume alone. Here is what makes big data, the 3 V's, volume. Healthcare wins big here with 2,314 exabytes of healthcare data. So let's check that box. Velocity. Picture a large ICU filled with very sick patients, each generating staggering amounts of real-time data. This adds velocity to the data since every second you have much more data added. Again, AI wins because you're uniquely keeping up with real-world velocity of this incredibly important data. And finally, variety. We saw in the introductory course data needed to predict outcomes in epidemics. This data comes from a variety of sources. Let's look at some of the sources. Satellite data, social media, crowd swarming by tracking cell phone locations, mining social media, ProMed Mail. Very different from just some columns and rows in a spreadsheet, I'd say. This is the variety of data needed to fulfill the definition of big data, and medicine does this in spades. Take an ICU again. You have EKG traces, CT, MRIs, numerical values for lab tests, mountains of data emanating from monitors, looking at everything from pulmonary artery pressure to heart rhythm and blood pressure. So when someone mentions big data, pin them down. It's not just big, it has to have the 3 V's. And this has been impossible to look at with routine statistics and data. With good, clean, well-formatted data, the world is yours. Even as a novice embracing machine learning, you'll have a huge leg up on the competition because of your willingness to embrace the future. And we'll teach you how to analyze some incredibly important data sets, including great cancer detection. So, first, let's look at some very popular machine learning tools from popular applications you may use right now. Facebook. Okay, we all love to upload our latest fun pictures of our friends. Facebook uses machine learning to predict what the names are that go along with the pictures. Netflix. Wonder why Netflix is so good at guessing what movies you want to look at next? They use machine learning, which learns from all the previous movies and films you've watched to make a best guess. Gmail. Notice how this popular email program decides which of your email is important, what's unimportant, and what's just plain junk? Again, machine learning determined what your junk mail was on the thousands of previous emails you have received and how you treated them. Now let's look at some great machine learning applications for healthcare from Health Catalyst. Reducing admissions. This is a huge problem for hospitals since they are often penalized if a patient has to be readmitted after discharge. Machine learning can reduce readmissions. Your doctor can receive daily guidance on who is at highest risk of readmission and what specific steps he or she might take to reduce the probability of readmission. Prevent hospital-acquired infections. 40% of patients die when their central line becomes infected. Now doctors can follow the patients at highest risk and work to reduce these factors. Reduce hospital length of stay. Long hospital stays cost insurance more money and also penalize hospitals. Machine learning helps to identify patients predicted to have longer hospital stays. Predict chronic disease. From high blood pressure to chronic obstructive pulmonary disease and cancer, being able to predict high-risk patients is at the heart of any public health strategy and good preventive effort. Machine learning helps identify those patients so doctors can come up with solid prevention and predict no-shows. As we saw in the introductory course, no-shows can cost doctors and hospitals millions of dollars and block times when other patients might be seen. Sophisticated machine learning models allow health systems to accurately predict who won't show up, when they won't show up, and how they might be rewarded to show up on time next time. Training data. The great intrinsic beauty of machine learning is that we don't have to teach the computer, which means we don't have to write thousands of lines of incredibly complex computer code. Instead, the computer trains itself. How? The computer muses over the data and looks for patterns in the data. Once it does, the computer finds a way of describing that data using a formula called an algorithm. So the heart of getting great results is having fabulous data for the computer to learn on. What's an example? Let's say you have 100,000 mammograms which have been read by the world's finest radiologists. Say half have tumors and the others don't. The computer then learns every last nuance of the images until the computer diagnosis matches that of the very best radiologists in the world. So in other words, when we feed in training data, we already know the correct answers and wait for the computer to learn every last important feature of the cancers. Then we go and test it to find out how well the computer's done. If there's a very clear, sharp distinction between cancer and no cancer, the computer has done a great job. But it can do what's called overfitting, which simply means the computer is drawing a crooked and curvy line through all the data to try to make up for bad data or a flawed method before putting it into production. Finally, after you've trained the computer and tested, you are ready to make decisions on real-world data, perhaps from your own hospital or medical practice. Now, let's look under the hood at the actual tools you'll be able to select for one of your machine learning projects. One of the biggest uses of machine learning is classifying data. Here are some examples from healthcare. Suggest a patient's diagnosis. Identify patients with high readmission risk. Automatically alert ICU doctors that the patient is developing life-threatening infections. Set the thresholds for abnormal lab results. You may set up your machine learning models to give you specific yes or no answers. This is called a binary classification. Cancer, no cancer. Diabetes, no diabetes. This binary classifier gives you only two possible answers, the yes or no. You may also output a range of answers, as we saw in the introductory course with the breast density case study, yielding a variety of answers. High tissue density may mask early cancers. Breast tissue may be classified as entirely fat, scattered areas of fibroglandular density, heterogeneously dense, and extremely dense, which the system had to learn to read from the training data. We looked at a training data set which was enormous and consisted of approximately 2,500 patients with 10,239 multi-view images and high resolution between 42 and 50 microns. To solve the problem, these researchers used advanced machine learning techniques to score breast density. So this classifier had 4 choices. Now let's look at the individual tools you'll have as a data scientist using machine learning. You may use these tools individually, but more commonly you'll use them together to get a better result. At the end, your experiment will compare all the available methods and then choose the one which has the very highest accuracy and lowest number of falsely negative results. So these models are also easy to set up. With just a few lines of cookbook code, you have the freedom to try several different methods to see which yields the very best results. Sort of like watching a horse race. Machine learning remains such a mystery to so many healthcare professionals. We've had a look on an ultra-high level view on how data teaches a machine to learn. But how does it actually do that? Let's take a much closer look at several of the most powerful models and how they work. You may engage each directly, as you'll see in the cookbook section, or with an off-the-shelf program like Aug2, which can pick and choose the ones that work the very best for you. The most famous machine learning tool is the Support Vector Machine, or SVM. Let's look at several applications to healthcare. Autism. An SVM analyzed reach and throw movements in 10 normals and 10 children with autism. The SVM separated out the normal from the autistic children with 100% accuracy. Cancer genomics. High throughput techniques produce staggering amounts of genomic and epigenetic data. SVMs are leading to the discovery of new biomarkers, new drug targets, and a better understanding of cancer genes, as published in Cancer Genomics Proteomics. Novel drug discovery. SVMs can classify active from inactive compounds early in the drug discovery process. Schizophrenia. By combining neural image and SVMs, the journal Computer Intelligence Neuroscience reports that SVMs could distinguish normal controls from patients with schizophrenia with an accuracy of 85%. Colon cancer recurrence. An SVM classifier revealed 6 RNA signatures which helped in the prognosis of patients with recurrent. Drunk driving. What about an early warning model for picking up drunk drivers? Researchers looked at driving performance data and physiologic details, and SVM classification allowed them to successfully distinguish drunk driving from normal driving with an accuracy of 70%. I'm always on the lookout for drunk drivers. The usual telltale sign is they drive over the center line and then over the line to the edge of the road. Imagine, though, a machine learning system that could pick these drivers up and get them off the road even earlier. Hand arthritis. This can be tough to diagnose. Engineers, though, used an SVM to look at fingers, especially the proximal interphalangeal joints and the distal interphalangeal joints, and then stage patients with specific classes. The list goes on with many hundreds of examples. So how does the SVM do it? Remember, machine learning acts to classify cancer or not, drunk or not, active drug or no active drug, autism or not. SVMs yield a yes or no answer. SVMs have to draw the line between yes and no. Now let's look at how an SVM works. Have a look at this illustration. You have a bunch of blue triangles to the left and green squares to the right. Where's the dividing line between them? Well, you could find a lot of lines and they would all work. But if I drew the line here, then these new points would be in the wrong group. But which line really is the best? That is what an SVM classifier determines by finding the maximum amount of separation between the two lines that delineate the lines of demarcation for each of the blue triangles and green squares. The line equidistant between the two becomes the dividing line. This is called the hyperplane. I have to say that hyperplane is a very cool word, but it really just means this line of division. Now, even cooler is that SVMs can work in multiple dimensions. So in 2 dimensions, the data might be a complete mess with triangles and squares intermixed. But go to a 3rd dimension and presto, this is very clear. You see the line between the two. Actually, not a line at all, but a plane, as you can see in this illustration. Where does the name support vector come from? It's from the front line data points closest to the line. These are the vectors that support the SVM by helping establish where the hyperplane should be drawn, which is the line that provides the greatest separation. So what kind of data can an SVM handle? For this to work, the data must be clearly separable. It would not work if the data intermixed. You wouldn't have a curved hyperplane in our basic examples. Next, this works best when you have a long list of features, like a colon cancer problem we just looked at, but not many rows of data. The SVM is better at complex relationships than a linear regression and will be a big step up for you if all you've been doing up to this point in time is linear regressions. This is also great when you have many data outliers. You can see them here in this diagram. They just wouldn't matter in establishing an optimal hyperplane since they're so far away from the hyperplane. Downside, SVMs take a long time to properly train on data and require a lot of computing power. So when should you use one? So the real question with machine learning is when to use this tool. SVMs yield the best results when you have categorical result and continuous target variables. The coolest aspect is showing the significance of the predictors. That is, which factors prove to be the most important, like blood sugar and diabetes. SVMs are quick and fast to train. With the support vector line as clean as it is, you can have many outliers and missing data and still get good results. When not to use an SVM. If you're facing really complex or new problems you don't understand, you want to pull the most out of your data, the SVM is not the best tool. Random forest. This fabulous technique has decision trees at its root. Let's first look at a decision tree from the popular book Nadjaran Prashant, Demystifying Big Data and Machine Learning for Healthcare. This attempts to classify the patient as having heart failure or not having heart failure. Again, like we see in so many of the machine learning examples, a binary example, a simple answer, yes or no, sick or healthy, malignant or benign. But rather than establishing a formula to determine this, the machine goes through a series of questions. At each node, there's a branch point, which again is a yes or no. At the very bottom of a list, the node answers the question, heart failure or no heart failure. So a great place to start a heart failure decision tree is with ejection fraction. This is the fraction of blood that the heart pumps out in an individual heartbeat. Severe congestive heart failure might have an ejection fraction of 15%, healthy 55%. So the first question is your ejection fraction below 50%? If no, then you're out of the decision tree. You don't have heart failure. If yes, then we'll ask the next question. Do you have an echocardiogram showing a big left ventricle? If yes, you continue to the next one, and so on, all the way through these branch points to hit the bottom of the decision tree. So where does the term random forest come in? You notice that a decision tree looks like, well, a tree. Well, random forests have a whole bunch of decision trees, enough to make a small forest. And random, there's no fixed order in which these trees are activated. The order is totally random, hence random forest. What are the different trees? Various subsets of the data, so each can be examined in the finest detail. You might start with ejection fraction, another with large left ventricle, and yet another with shortness of breath on exertion. Then you let these random forests run and look at the results of each individual tree. The heart of the random forest merges these independent decision trees to give more accurate and stable predictions. This helps reduce bias and variance. Each tree focuses on a different part of data. The random forest is far better than any independent decision tree on its own. You can build multiple trees, all built independently on different subsets of data. In the end, the random forest works like a democracy, with voting for the winner based on majority voting. May the best data win. Logistic regression can be terrific for healthcare and a big improvement over the linear regression you may have learned in statistics. Logistic regression allows you to make a prediction about a specific outcome by estimating relationships among variables. You're familiar with a linear regression, which shows you values along a continuous line. Just pick an x value and it shows you the y outcome. Logistic regression operates quite differently by offering you a simple true or false answer rather than picking a point off a line, yes or no. That all has to do with the way the graph is set up. Here's a graph of a linear regression. Again, pick any x value along the line and you pick the y solution. However, this line is continuous and could go well below zero. Logistic regression uses a sigmoid function. As you'll see, too, in deep learning, this has a special value. Simply put, the sigmoid function does not allow the top value to go above 1 or the lowest value to go below 0. This, in effect, forces an answer. 1 becomes yes, 0 becomes no. This is called a binary solution, yes or no, cancer or no cancer, heart disease or no heart disease. What I like best about logistic regression is that it's a very transparent model. That means I can learn which features are the most important, which allows me to impact the clinical practice of medicine. Many people see algorithms as a secret formula, but with logistic regression, you get to look behind the veil and see what the most important variables are by looking at their odds ratios. As you get ready to explore other techniques in deep learning, logistic regression gives you a quick benchmark. As a data wrangler, you want to consider when not to use LR. You want to avoid it if you have big data sets with either long columns or large numbers of features, many missing values, or poorly formatted data. You will also want to avoid LR and choose a straightforward linear regression if you have continuous variables, which are perfect for linear regression. So here's a perfect example of using logistic regression to get a yes or no answer. Is a thyroid nodule benign or malignant? Publishing in PLOS ONE, these researchers looked at 525 pathological nodules using conventional testing, which included conventional ultrasound, strains, elastosonography, and contrast-enhanced ultrasound. Logistic regression allowed the researchers to pick out the most important features which were statistically related to the diagnosis of the nodules. What do they pick out? Calcification, suspected cervical lymph nodes, metastasis, hypoenhancement pattern, margin, shape, vascularity, posterior acoustic, echogenicity, elastography score. LR allowed the researchers to establish a model could then predict malignant from benign. Rural health. Here's another example of the simple yes or no answer for the American Journal of Preventive Medicine. Are rural residents less likely to obtain recommended preventive health care services? National data from the 1997 Behavioral Risk Factor Surveillance System, BRFSS, and the 1999 Area Resource File were used to evaluate the adequacy of preventive services obtained by rural and urban women and men. The research used nationally accepted preventive services guidelines from the American Cancer Society, the U.S. Preventive Health Services Task Force, and Healthy People 2010. The logistic regression models were developed to control for the effect of demographic factors, health insurance status, and health system characteristics. Results: rural residents were less likely than urban residents to obtain certain preventive services. With this knowledge, doctors and public health officials could increase rural preventive services utilization to confront the special challenges that rural health presents. Naive Bayes. Bayes' theorem describes the probability of an event based on prior knowledge of the conditions. For example, if heart disease develops with increasing cholesterol, blood pressure, and age, Bayes' theorem allows you to look at your individual risk, but it's more accurately assessed if you look at this deep background knowledge. So bottom line, Bayes is allowing prior knowledge to be factored into the algorithm. Let's look at a published example from the medical journal in the article entitled Detection of Cardiovascular Risk Levels for Adults Using Naive Bayes Classifier. Objectives. This paper proposes a mining model using naive Bayes classifier that can detect cardiovascular disease and identify its risk level for adults. Primary risks were diabetes, levels of lipids in the blood, coronary artery function, kidney function. Results. The classifier achieved good performance for risk level detection of cardiovascular disease above 80%. So to be clear, it wouldn't make much sense to design a cardiovascular risk system without taking into account the tens of thousands of previous studies in the large-scale studies like Framingham Heart Project or the Doctors and Nurses studies as background, and where tight relationships have already been developed for key risk factors such as family history, cholesterol, and high blood pressure. KNN, K nearest neighbors, is just like it sounds. The tool will find which neighbors your data is closest to. The assumption that KNN uses is that your nearest neighbor will have similar data properties. Take several flocks of birds. Which bird does the one you're looking at belong to in terms of two different flocks? It's a straggler, it's between them. KNNs measure the distance between each of the flocks in the sky and this bird, and then determine what the K nearest neighbor is for this classification example. So let's look at this example of heart disease. You can see two established clusters. KNN will now try to determine which of these two groups this newest point may be included within. So the KNN learns from the training data you feed it. Enter a new point and will calculate the difference between these new points and the training data. Keep in mind that the key for training data is to already know what the results are. KNN then selects the K nearest neighbor and assigns it to a class. I love KNNs for determining data patterns and recognize them, often yielding surprising results. Boosting. This aggregates a number of weak models. Boosting learns from its mistakes with each iteration. If your results are nearly a coin toss, then gradient boosting can improve your results. Boosting performs an amazing function by taking the values that don't quite work in a data series and then using them for the next level analysis. Platforms. Now that we have had a look at the basic tools machine learning uses and some terrific examples from healthcare and medicine, let's look at the platforms available to you to begin your own projects. So first of all, there are what I call true plug and play platforms like DataRobot. You can sign on and get a free trial, which I'd encourage you to do. So DataRobot advocates for automating machine learning and creating a new class of citizen data scientists with the power to create advanced machine learning models. Now, this is all without having to learn any code or understand when and how to apply certain algorithms, which is what I love about it. It's a very attractive interface. DataRobot claims that scientists are also more productive at repetitive steps in the model building process if they're automated, allowing them to use their own unique skills and expertise for selecting and fine-tuning models. So DataRobot has some terrific healthcare examples, including healthcare administration. So here's some of the examples which you can actually use on the platform yourself. Predicting ICU and emergency department utilization. Determining which patients are less likely to take their medications. Alerting doctors about patients who may be at risk for hospital-acquired infections. predicting patient length of stay in hospital. Those who could benefit from this would be current chief digital officers, chief information officers, business and department heads. Here's a brief demo of how it works. So again, if you download this model, fire it up, this is what it would look like, and I encourage you to do so. This is fascinating to watch as it pulls in many of the tools we talked about, from support vector machines to random forests, where you can see it work on the right side of the screen. This is a far more comprehensive approach than many data scientists would be able to deploy without years of experience. There's even a complete quality control dashboard. You can try Data Robot for free with a 14-day trial. Microsoft Azure. DeVry uses this platform, and it's part of the DeVry machine learning course. This does take several weeks of instruction for you to get up to speed. However, I would love to show you the plug-and-play features as they're added, and then the training and testing features here as well. Here's a quick tour thanks to one of DeVry's fabulous faculty and the biggest Python enthusiast I know, and a great friend.
Hello and welcome to creating a machine learning experiment with Azure Machine Learning Studio. To get to Azure Machine Learning Studio, you go to studio.azure.ml.net in a web browser. You log in with a Microsoft ID. When you sign in, it'll take you to all the experiments that you can create. So when I log in, I'll have several experiments, and I'll show you how to create a new experiment. So what we'd like to do is use one of the existing data sets in Azure Machine Learning Studio. So I'm going to click the New right here. And this will give me the option to create a new blank experiment. So I'm going to click Blank Experiment. And I'm going to name this Diabetes Classification Experiment. Now what I'm going to use is actually a data set that is quite commonly used for diabetes classification, and it's already in Azure Machine Learning Studio. So I'm going to click Samples, and if I scroll down here, you see there's many different samples. I'm going to click the Pima Indians diabetes data set. Now I'm going to right click on this data set, and I'm going to visualize it. I want to see what kinds of fields exists in this data set. I can see there's 768 rows and 9 columns, and these are the different fields that we're looking at. I can click on different fields here, and I can look at the statistics on the mean, the median, the standard deviation, age, and variables, body mass index. So I can see all of the data that exists here, and the class variable 0 or 1 actually determines whether the diagnosis, where 1 is diabetes and 0 is non-diabetic. Okay, so we're going to try to do, we're going to do something fun. We're going to actually use a k-means clustering module in order to determine if the person in this experiment has diabetes or not. So let's go ahead and do that. When we create machine learning experiments, one thing we need to think about is the data. Is our data good data? Do we have any problems with our data? Do we need to do anything to our data? And we do. So I'm going to go to Clean Missing Data up here in the search and drag it on here. Now one of the issues, if I look at this data set again, is that some of these values are 0. Like for example, blood pressure is 0. Well, that's not correct because blood pressure isn't actually 0, and the fact that it's 0 might cause problems and skew our results. So we need to actually clean some of this data. So I'm going to click and drag from here to here. And I need to show that I want to clean that data. And so the way I can do that is with this Clean Missing Data module. So I'm going to click Launch Column Selector. And I'm going to pick a few columns that I want to make sure I can remove the missing data. So I'm going to start typing. And then I'm going to pick the blood pressure. I'm going to pick the skin thickness. I'm going to pick the BMI. I'm going to pick glucose and insulin. Okay, so let's check all those. So those are some things I want to do. Now, how am I going to look at this missing value 0 cleaning mode? Now, there's a variety here that you can look at the different cleaning mode. I'm going to use this substitution replace using, and this is a different way where you can iterate to find a good value here. Columns with missing values I'm going to remove. Okay. So the next thing I want to do, because we want to clean our data, and this is often something you need to do when you have a data set, is next thing I'm going to edit my metadata. So I'm going to choose edit metadata. Because what I'd like to do is I'd like to set a label. And the label I'm going to set here is the class. So I'm going to drag this in here. And I'm going to type in class. And I'm going to specify that this field is a label. All right, this is looking really good. So I want to start with my clustering, and I'm pretty excited about this because we want to see how we can cluster this data. So I'm going to type in here, and I'm going to grab a k-means clustering, and then I'm going to also grab a sweep clustering. I want to assign data to clusters. And I'll go over what all this is in a minute. And then evaluate model. Okay. So I'm going to drag a couple different things to different places. So the first thing I'm going to do is drag my edit metadata here, and I'm going to drag it over to my sweep clustering. And you can show where it says the green dot. I can see where I'm going to drag it. I'm also going to drag it to the assign data to clusters. Okay. And I will set parameters in a minute. And I'm going to drag the k-means clustering into the sweep clustering. And then I'm going to drag here, evaluate model, and assign data to clusters. So we're setting this up for our k-means clustering, and we're going to look and see some of these parameters. So if I click on here, I'm going to create trainer parameter range. And here's the thing, I would like a range of 2 to 10. Because I'm not sure if 2 parameters are best. I mean, how many clusters should we have? Okay. I'm going to use the label column. Number of sweeps, let's go with 15. And you can choose however many iterations you want. So this is looking pretty good. This is my k-means clustering. Okay. Now here for my sweep clustering, what I'm going to do is together these two, the sweep clustering and the k-means clustering, they work well together. I am going to use the sweep clustering model and connect it here, as you saw, with the k-means clustering. And I'm going to configure it now. I'm going to use this. I'm going to use this Dave's Boolean option here for the metric. You can choose entire grid or random sweep because I want the whole thing, like 2 to 10. How many clusters do we really want? Okay. And then I'm going to launch my column selector, and I'm going to select the columns that I'm going to use. Okay. I'm going to use plasma, skin, Kmax index, age, and class variable. There should be 9. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like we've got them all. So this is looking really good for our model and how I want to specify what my model is going to do. Okay, so I would like to run this, and I wonder how many clusters I'm going to get. How's it going to cluster these? So I'm going to click first I'll save my model, and after that I will run this. It'll take a few minutes to run because it's going through and testing and doing several iterations. So our model has finished, and let me go ahead and look. The evaluate model, you can see I have this evaluation results to visualize it, and it shows me the different clusters. There's 2 clusters here, average distance to center of the cluster. I can look at visualize the clusters here. I can see cluster 1 and cluster 0, a principal component. And this principal components visualization can really understand how the clusters are related to each other. And so you can look at the different outsets of the outputs of the data to see, how does it look? What does the data look like? If I look at the data. And this is, I find very interesting because this is the class variable and this is the assignment, so you can see how they're a little bit different here, the assignment versus the class variable. And you can actually check this out. And I'm going to show you a way to actually I'm going to drag this SQL transformation. And what I'd like to do is provide some SQL to look at the results more clearly. Okay, so I'll drag this on here. And I'm going to write some code. Now we know here from our code that we want to look at class and assignment. So class, actually, let's get the exact name of the data set. Hold on. The exact name of the field is class variable 0 or 1. So let me write that. Okay. And the assignment is where is how it was assigned by the clustering model. Okay. And then I'm going to do a group by and I'm going to group by assignments. So this actually can show me in the code the count, how many there are. So let me go ahead and run this again with my SQL transformation. So our code is finished running, and if I look at this, I want to visualize this. This is very interesting. When the class variable is 0, the assignments are 0, that's 207. When the class variable is 0, the assignment is 1, it's 293. So you can see how, like this kind of a matrix where I can see, how it has assigned based on the actual class variable and how many there are. Okay, and you could look through that in more detail.
Thank you, Gina, for a terrific look at Azure Machine Learning Studios. Grateful for your taking us through this. Gina has a whole course in machine learning at DeVry. Now let's take one last approach, and that is the cookbook approach. As a student learning just one proprietary platform, you won't have the capacity to then switch to another one easily when you land a job. Employers will want you to have a general familiarity and to know the common vocabulary. So if you learn Microsoft Azure systems as an example, you may land a job using Google TensorFlow, which you'll then have to learn. The best and most universal approach is to use a common data science language, Python, and the key Python libraries. We're going to take this cookbook approach, which is literally just as good as a codeless platform, or better, because you can dive under the hood and look at the key functions and fully understand them. In this course, I'll show and explain the code and run it for you. In the follow-up course, we'll teach you to cut and paste that code into a working platform where you can then modify it to run your own program. Python. I just love Python with its simple, sparse coding and fun applications. Across a variety of sites, Python ranks as the #1 language for machine learning and deep learning. Python ranks second overall, just behind JavaScript. Let's look at why. Python has a tremendous number of features and a robust quality of code, which is easy to debug in development environments like Anaconda or within Microsoft Azure. I find Python incredibly productive since I spend so much less time coding and debugging. Even though it's a very technologically advanced, it's a very easy and logical, even fun language compared to, say, Java, which can be incredibly difficult for a beginner. So difficult that Stanford has dropped Java as its initial computer language course. Libraries. However, Python's greatest strength is the extensive libraries for machine learning. Think of these libraries as apps like you buy from the Apple App Store if you have an Apple computer, or iPhone stores, or if you have an Android device. The only difference is they don't have the wonderful graphical interface. Instead of pushing buttons, you'll have to enter the actual values by hand. But they are just as slick, much faster, and far, far more powerful. So at the beginning, I made a promise, and I'll keep it. You won't have to write a single line of original code. Why? Fortunately, the Python libraries do it all for you. So, what is a Python library? This is a collection of functions, formulas, and methods that allows you to achieve many of the machine learning goals you have without actually having to write code. For instance, NumPy handles numerical operations. Another manipulates images. A third does natural language processing, like you may find with Siri. This changes how we think about how we write code. For those of you who have written a lot of code in the past and mastered computer languages, you remember laboring for weeks and weeks trying to write loops, what-if statements, and spending countless hours trying to write hundreds of lines of code, and then laboriously debugging for errors that aren't really apparent. I helped write complex machine-level code for advanced sports science physiology and biomechanics applications. I got to tell you, it was tough stuff. There are a lot of all-nighters there. So first, let's look at code written on a low level, meaning closer to machine level and requiring great skill, complexity, time, and knowledge. You can see the tremendous complexity and many lines required, plus an in-depth knowledge of matrix algebra and all of the mathematics behind it. And trust me, those formulas can get pretty complex. Now, let's take the example of an artificial neural network in a very high-level library called Keras. I've literally memorized these 10 or so lines of code. Memorize it yourself, or just cut, paste, and fill in the variables and let it rip. Just a few lines. Here they are. Import NumPy, import pandas, import Keras, import sequential, import dense. That's the first part, just that simple. Now just enter values for each of the fields. As an example, how many layers do you want? Here's what it looks like in the code. And here are those layers in a TensorFlow example. So as you can see, the heart of what you really need to know is this. You need to be able to introduce and change variables in your model. Whether it's a polished, off-the-shelf application or a Python formula, the variables are the same. And these are what we will focus on. But first, let's look in greater depth at the Python libraries. There are 137,000 libraries and 198,826 Python packages for a huge variety of pre-built solutions, but just a small and really useful and easy to use number for machine learning and the deep neural networks that we'll cover in the next course. Scikit-learn. This is a premier machine learning application with everything you need. What I like best about Scikit-learn is its easy integration with the two most basic Python languages, NumPy for numerical calculations, and pandas, which you can think of as a spreadsheet for machine learning, which offers the data structure and operations for manipulating numerical tables and time series data. However, instead of calling it a spreadsheet in machine learning, the parlance is a data frame. Scikit-learn comes with the support of various algorithms such as classification, regression, clustering, dimensionality reduction, model selection, preprocessing. Scikit-learn is very easy to learn and highly flexible. Scikit-learn focuses on data modeling and not on other tasks such as loading, handling, manipulation, and visualization of data. Best yet, you can use scikit-learn for end-to-end machine learning, from the research phase to the deployment. For a deeper understanding of scikit-learn, you can check out the scikit-learn tutorials. I use scikit-learn to look at the variables and get a sense of how much sense they make on their own. First in scikit-learn, then proceed with the models. NumPy. As you'll see in the deep learning course, you'll need to feed arrays into your models. NumPy makes the execution of these projects much easier. This is your main numerical calculator. Pandas. This is a fast platform for creating the data structures you'll need in machine learning, and even allows for time series data. For medical and health applications, time series is vital since you need to take measurements over time to follow how a patient is trending, either for better or for worse. You can easily organize, explore, represent, and manipulate data into the data frames necessary for artificial intelligence. Thought of as an Excel for machine learning, you'll learn how to create these data frames. In fact, Pandas actively supports Excel, which I still find is an excellent first stop to organize your data, looking for missing values, duplicates, and starting to clean your data. A favorite instructor of mine told me, if you can organize your data into an Excel spreadsheet, you can run it. Keras is my favorite Python library and helps you implement the key features of creating neural networks, including layers, functions, and optimizers. We'll see this in greater detail in the course on deep learning. Keras works for a whole range of deep learning tools, including artificial neural networks, convolutional neural networks, and recurrent neural networks. Matplotlib, his favorite tool of mine, contains a comprehensive library for creating a wide range of interactive animations in Python. Have a look at these fabulous animations. As soon as you open up the library, you'll be tempted to play with it for hours. Here are some examples. CT plot of the brain, so important for neurology and neurosurgery. Contouring, histograms, and the coolest thing, three-dimensional plotting. You might use this when considering SVMs to see if a 3D model makes better sense of your data and allows you to create a hyperplane. I find it fascinating and vital to use libraries like Matplotlib that allow you to look at and analyze your data before you begin machine learning. Ellipses. This supported the Phoenix mission to Mars. There's also very standard fare such as pie charts, tables, and scatter plots. And it creates these so that they're publication-ready graphics. So if you want to plot out your data to see what it looks like before starting a machine learning project, this is a great set of tools. You can plot several different variables in two-dimensional graphics. TensorFlow is a machine learning library and gives you an immediate iteration of machine learning models. You can create, manipulate machine learning models, and debug them easily. This is the companion, TensorFlow Playground for deep learning, which you'll love and you should start playing with as soon as you can. So what's a tensor? This is Google's name for a matrix, and this is a three-dimensional tensor or matrix, which will be output, and it will look something like this, where you can see that you have rows across, but you also have rows back. So to be clear, you'd have an X and a Y and a Z axis to take this matrix and then put it into action. Seaborn is a Python data visualization library. With this, you can produce extremely attractive drawings. I love Seaborn for its ability to view the structure of really complex data sets. Since all the machine learning is working with multiple variables, Seaborn is an important way to look at how they are related to each other before constructing your model. PyTorch is a Python machine learning library. This is a terrific application if your projects involve computer vision and natural language processing. This is a lower level library and does require more coding experience, though it is lightning fast. How do you access them? It's literally as simple as writing import and then the library name. For example, import NumPy imports NumPy. Import Keras imports Keras. That's it. Okay, now that we have a good chance to look at the Python libraries, let's use them in a machine learning example in healthcare. Let's look under the hood at the actual instructions used to run a support vector machine on a model of heart disease. I found this on the GitHub site by just searching SVM, or support vector machine, and heart disease. GitHub is a huge repository of code you can easily download and use once you have mastered a development environment, or IDE as we call them, such as Jupyter Notebooks. IDEs provide a source code editor where you can completely open up a file from GitHub and a debugger if you want to change any of it. I chose this model. Just click Download Code, then open Jupyter Notebooks and import the code in the dataset. It's really just that simple. If you don't have an Anaconda setup, here's the link to a short course at DeVry, which is free to you and will show you how. Or you can just follow along and watch. No need to code. In later courses, we will take you through the whole setup. I cut and paste or copy over these lines of libraries to import these 4 libraries just like this. Import NumPy as NP, import Pandas as PD, import Seaborn as SN, import Matplotlib, PyPlot as PLT. The simple import command is all it takes to bring these libraries on board. Each is assigned an abbreviation. We've seen how sklearn is the key Python library for machine learning. Now look at how incredibly easy it is to set up your model for support vector machines. From sklearn, preprocessing, import normalize, imputer, standard scalar. This allows you to preprocess your data. From sklearn, model selection import, train test split splits up your data into training and testing. To be clear, the training data selects a subset of data to train your model. Then another subset of data tests the data to see how well the model works before you put it into use with real data. From sklearn, import SVM imports, the support vector machine, which is the actual application that will run your support vector machine. It's really that incredibly simple. These next instructions load 3 sets of data from Cleveland, Hungary, and Switzerland. You can look at each of these data sets individually. You can see across the top the various risks like age, sex, blood pressure, fasting blood sugar. The final column in the Hungarian data is a 1 or a 2, and that represents that you either have heart disease or you don't. So in other words, the data you're feeding in already knows whether the patient has heart disease or not. That's how your SVM will know in the training set which patients had heart disease and which did not. Next, Matplotlib allows you to visualize your library in a variety of ways. For instance, in the heat map, you can see the tight correlations between age, sex, and cholesterol. Finally, it's time to set up your model. So first, some data wrangling. As you can see, the missing values, which are labeled NaN, are replaced with a mean. Next, you train and test the data. Then build your classifier to predict heart disease or no heart disease. Then finally, you look at the accuracy of your prediction to see how well you do against other models. So an accuracy score of 65% is, well, not that great. Why? Remember, an SVM does better with a huge range of features, which this model doesn't have, and a short column of data, again, which this model doesn't have. In the deep learning course, we'll take another try with a much more powerful tool. As you can see, this took just a few minutes to copy all of the code in and run it. Clearly, there's a lot more detail, but I want to give you the confidence and convince you that you can construct machine learning models and run them literally in a matter of minutes. As you see, what's really needed here is good, clean data, which we're able to wrangle, and a well thought out strategy and choice of machine learning tools. So the question is this the right strategy for this data? What does the data look like? Can you see correlations like age and sex to heart disease? Data wrangling. Data wrangling, the biggest piece of getting machine learning platforms to perform well is having clean, well-organized data. As an example, during the COVID-19 outbreak, a state health authority would fill out a paper form for a COVID test with the results. Then the CDC would copy it again on paper, and finally it will be linked manually into a computer, all slowing the speed for final results and potentially creating a myriad of errors along the way. If you're running a healthcare organization or even medical practice, you want to set up really clean, error-free, well-organized data. Many careers will be built around data wrangling or prepping data for entry. With the fast speed of artificial intelligence, increasingly there will be less need to code and program since you will have off-the-shelf applications, and your career will focus on preparing clean data in elegant data frames that are ready for machine learning tools. You'll also understand the data by using apps like Matplotlib to see data disparities and gauge just how good your data is, and importantly, which of the fabulous machine learning tools are best suited to your task. As we have seen, data with huge numbers of features, but relatively few rows of data, may work best in a support vector machine. I just love this part of data science and machine learning, using all of the fabulous graphical tools to appreciate what our data does best and how it is likely to behave. We'll have separate courses on data wrangling and how best to find how you clean up your data, enter the data in the computer, and then test it, its accuracies, and most importantly, compare your results across a variety of methods to see which ones work best with your data. And that's really the heart of this. You want to be able to take all of these various tools, just see what works best. You can be agnostic, just try them all because they're that simple. Dealing with missing values, often a big problem with healthcare records, deleting duplicate records, looking for imbalanced data. For instance, if your training data is trying to diagnose breast cancer among 5,000 records, but there are just 10 cases of breast cancer in the data is wildly imbalanced and of no benefit in training. Looking at trends to be sure they make sense would be amenable to modeling. Selecting the best features that are most likely to yield good results. Well, great. So thanks for sticking with me through this. That's an overview of machine learning. As you can see, you have several choices in terms of implementation. A robust commercial application like DataRobot, large-scale development environments like Microsoft Azure, Python and its libraries in a development environment. Knowing this, you'll be able to carry on effective conversations with your employer on strategies and have a framework to get good at machine learning quickly. Let's look at the kinds of real development jobs available in machine learning. This site, Developers for Hire, suggests a number of exchange networks with direct links for entry-level jobs. Here's how they rank them at the beginning of 2020. Stack Overflow, Hired, GitHub, TopTal, Scalable Path. So to finish this introductory class, let's look at the top applications in machine learning for healthcare in real companies with real jobs. We'll see you in the next introductory course on deep learning and healthcare. So here they are, real companies who use machine learning in healthcare and are hiring, who may be looking for you. You can view the jobs right on these sites. Take Quotient Healthcare, hiring in data analytics, design, US development and engineering, project management, even internships. Quotient's business is smart electronic medical records. Kinetsky employs machine learning to predict and treat illness. PathEye helps pathologists make quicker, better diagnoses. Quantitative Insights speeds the diagnosis and accuracy of breast cancer. Microsoft's Inner Eye project differentiates between healthy eye and tumors by helping with the analysis of radiotherapy and surgical planning. Pfizer has developed an AI-powered platform to model small molecule drugs. InSitro is using machine learning with advanced lab technology to develop drugs at a lower cost. Biosymmetrics helps with data pre-processing to improve accuracy and save time from biopharmaceuticals to precision medicine. Well, thanks so much for listening. I hope you're as enthusiastic about machine learning as I am, and remember, it can be quick and simple to get up and get started and start to really understand this wonderful field. In our next course, we'll have even more fun as we dive into deep learning, the basis of much of current AI. We'll use a ton of healthcare examples and show you all the key neural networks. If you're sold on machine learning, you can continue on your own on the Microsoft platform or enroll at DeVry for a full career-level series of courses in data science and machine learning. Good luck. You're going to crush it.